All right, now let's talk about one of the last topics in the syllabus for statistics, which is called as standard deviation, also called as SD. And again, it's going to be a part of the absolute measure of dispersion over here. And it's going to be a continuation video from variance. So if you're not seeing the previous part where I've covered the variance, you should cover that because standard deviation and variance are kind of related. And for knowing the variance itself, I would recommend you watch the mean deviation video, but at least watch the variance for sure on this one. So in this episode, we're going to just cover this part, standard deviation. It's going to be a short video because a lot of concepts are going to be borrowed from variance, and then we'll move on to the next episode. All right. So standard deviation, again, like I explained in the last video itself, it pretty much tells how the numbers are spread, and that's the whole concept of variability. So anything that has to do with the measure of variability, it just talks about the pattern or the way the numbers are distributed or the given values are distributed with respect to some point, typically a mean point. Okay, that's what it means. And it's represented by this symbol called as sigma. Like I said, even this is called as sigma, sigma in Greek, and even this is called as sigma. It just the difference is this is for the uppercase representation, this is for the lowercase representation, and this is used to symbolize summation, addition, and over here this is for if it's not with the square, it's for standard deviation. If it's with the square, then it's for variance. That's what it means. Okay, so nevertheless, so and if you want to have some extra reading on standard deviation and the definition, you can go through this link called Maths is Fun. That's very good. I've referred it extensively for putting up these episodes. So what is the definition of standard deviation? It's very simple. Standard deviation is nothing but the square root of variance. So you don't have to have any special tricks to calculate the standard deviation. All you need to do is first calculate the variance, and then you just take the square root of that, and that will give you the standard deviation. So this is what is standard deviation all about. If you see here, standard deviation is nothing but the square root of variance. Square root of variance itself is represented by sigma square. So if you do a sigma square, all you get is a sigma. That's what it is, standard deviation. And interestingly enough, textbooks first, like for example, I covered the mean deviation first, and then I covered variance, and then I'm covering standard deviation. If you see the textbooks, they will cover the mean deviation, then they'll cover standard deviation, and then they'll cover variance. I don't know why they do that. It's very confusing. If you just follow mean deviation and then from there you take variance, it makes connections because you know why you need to do this. And from here again, you make another connection on just taking the square root of variance will give you a standard deviation. Okay. And if you want the statistical formula, this is a formula, but I would recommend not to memorize that. All you just need to memorize is one formula for mean deviation. And in mean deviation, if you replace the absolute value with a square value, you get variance. And then if it's the same formula, if you do put it under the square root, which is what this pretty much is, it's going to be your standard deviation. Pretty much if you see, if I had put a vertical bar here and no square, it would have become mean deviation. But if I just replace the absolute values and put back the square, it becomes variance. And if I put back the square root, it becomes standard deviation. So as simple as that. And in terms of steps, I copied the same example from the last time where we calculate the variance. So for calculating standard deviation, you still need to go through all the steps till you calculate the variance. And in the final step, whatever is the value, you just take a square root of that. If you see here, I'm taking the square root of that, and then you get a lower value, which is going to be your standard deviation. So that's exactly what's going to happen. So no other differences. If you see here, standard deviation is equal to the square root of variance. You take it under the square root and you take the value. And if you see the last step, for the first 5 steps are exactly same for calculating the variance. There is no difference in that. You just add the last step for standard deviation or SD, where you just take the square root of the variance to get the standard deviation. And that's how you kind of get it. Very important concept from a syllabus standpoint. You'll definitely get questions on both variance and standard deviation every time. And a related topic is also a coefficient of variation, which we'll see in the next video. Again, it's a very simple topic, but this and this will form mostly 50% of your marks. So focus on that one. So that's all I wanted to cover. Just remember, standard variation is square root of variance. And an interesting thing, you don't have to remember from an exam standpoint. So you can skip this portion. But if you're curious, why should not we kind of just take the square root like we did in the variance over here. Sorry, the square. Why should not we just stop at taking the square? Why do we even need to get into a square root? What is the reason for that? And the reason is pretty simple if you are interested to know, okay? I'm going to give you another example. Let's talk about average life expectancies and standard deviations, and I'll tell you what it means. So let's take this example. Let's take the example of, say, Australia. Let's take Japan, because the life expectancy in Japan is very high, and that's very interesting. So let's take the example of, say, female life expectancy. So a female life expectancy in Japan is 87 years, okay? And this is in years. And what does it mean? An average Japanese woman, a lifespan is 87.1 years. They can stay up to this. They can stay up to 87.1 years before they die. And if you just compare, what is so magical about that? For India, I think for women, it's in 70s. I would say 71 or 72, and for men, I think it's 69 or 70. So it's that low. So we almost are 15 years behind in terms of life expectancy for different reasons, but that's a different topic. So that's a beauty. If you see all these ages here, even for women and for men, they're really top class in the world, at least the Japanese figures are higher. This could be older values, but Japanese figures are definitely higher. If you see the female life expectancy, Japan is the highest in that one. Even in the world record, I think the Japanese woman, the longest living Japanese woman is 102, 110 or something like that. Anyway, so the point I'm trying to make over here is, let's take this example of why we need to have a standard deviation and why can't we just stop our life after calculating variance. So let's say we take about a Japanese woman, and the average life expectancy of a Japanese female is 87.1 years, and the unit is years, okay? And the standard deviation is given as 12.7. So first, let's understand what is the meaning of this. So what we're saying is, if you take the patient population of Japan, let's say let's roughly 125 million people, a very small country, right? Just 125 million people. In perspective, it's like half of Uttar Pradesh population, I would say, roughly half of Uttar Pradesh population. But anyway, so if you take the 125 million people, and let's assume that half of them are women, so roughly say 60, let's take 60 million for namesake. 60 million people are women, and 60 million people is nothing but 6 crores if you want to just know the Indian this thing. Okay, so 60 million people are women. So on an average, we don't know the exact living age of individual. On an average, each Japanese woman live happily for 87.1 years. Okay, and the standard deviation is 12. The value is 12. So what does it mean? So on an average, they're going to live up to 87 years, and the deviation is going to be 12.7. That means, at the most, even if you're wrong on this number, you will be plus or minus this number. For example, either this number can be short by 12.7 years, or it could be bigger than 12.7 years. So if you just take 12 for the sake of mathematics, so if you just remove this, if you just take 12 plus or minus, standard deviation is plus or minus 12. So what it would mean is, we know that the average age is 87, but even if you are wrong, at the most, the range where you can go wrong in your estimates is 87 minus 12 is 77, 75 on the lower side, and on the higher side, 87 plus 12 is going to be 99, right? So what it means is the room for error or the deviation from this age could be in this range. So if you're wrong, you will not be more wrong than this plus 12 or minus 12. So on an average, it's going to be 87 years, but there could be some instances where there are going to be differences. So in the lower case, the lowest age where a Japanese woman will live or survive before she dies is going to be 75, and the highest age where a Japanese woman lives and overshoots 87 is going to be 99. So this is your kind of tolerance band or the standard deviation. So that's the standard deviation. That's how far you will deviate from this mean number. That's what it kind of means. So that's kind of the number here. So that gives you a context of what is the standard deviation, right? Now the question is, why can't we just have a square of that number and then still go with that? The problem is, if you take this number, standard deviation, let's say this is the sigma, and I'm going to draw a column here, and we're going to put a variance here, right? and we know variance is nothing but a squared number, sigma square. So if you take this 14.5 or even let's say 15, if you take this number and if you try to calculate the variance for that, it's going to be 196 if I take 14, or if I take 15, I think it's going to be 225, right? That's going to be because it's a square. But if you do this, it does solve the problem of what we had in the mean deviation, where we need to take the absolute value. So that problem gets solved. But if you see, if you take this values over here, right? In this case is 196. In the case of 13, it's going to be 169 because we're going to square it off, right? So what is the problem in that? So the values look unusually bigger to manage, right? Because you're talking about age, and the values are getting bigger and bigger. And if for some reason, if it's a different value, not age, if the standard deviation is a bigger number, let's say standard deviation is going to be 1000, then it's going to be 1000 square. So variance can just go very big, and it's going to be hard for us to manage in terms of pure mathematics. That's the first problem with that. The second problem, which is more important, is it does not even make sense. There is no intuition. If I tell, hey, the variance for the age group is 196, what does even mean? We're talking about age, and when we say 196, what does it even mean? There is no intuition. We know that people are not going to live that longer. At the most, they might survive is 100, 110, 105 or stuff like that. So if you say 196, that is specifically in the context of India, that number looks like insane. It doesn't provide you any intuition how big that number is and what is the purpose of that. No, it solves problems, but it does not give any intuition or make sense. That's another problem with that. Okay. And the last problem is what's going to happen. It loses the units. For example, the age, let's say for this one is 81 years, right? We are putting 81 years. But when we square this, and the deviation is going to be 13.8 years. So it's going to be plus or minus plus 13 or minus 13 years. So that also is fine. But when we multiply the standard deviation, this years also get multiplied. For example, if it's in centimeter, then it becomes centimeter square. Then it's almost like an area. That's okay. You are given in one dimension and you're getting the area. But if you're going to measure in years, and then that years becomes year square, what does it even mean? I mean, if you're squaring a unit, does it even mean anything, this unit of measurement? So if you say, what is the variation for this particular person? We say it's going to be 169 square years. Does it even make sense? So it also messes up the unit of measurement. So these are the three big problems in case of variance, although it solves some of the problems and it is still used in a lot of cases, which we can talk about in a separate video. But these are the three main reasons why we need to have a concept called a standard deviation, where we calculate all the way through the variation. We'll go through the variation process or calculating the variance. But finally, we take the square root of that. So what happens is when you take the square root, all these problems get solved. For example, the number becomes smaller, because if you see here, let me get rid of this. So if you see here, the numbers get smaller because I don't have to talk about big numbers. If I ask you what is the standard deviation, you're talking about in small numbers. Hey, the standard deviation is going to be plus or minus 14 instead of saying 196. That's one part of that, right? Secondly, it makes sense also because 14 years is something we can imagine. Okay, someone can live up to 100 years. 81 plus 14 is going to be 95. So we can still comprehend the meaning of that. And plus, it does not lose the original units of measurement. It is standard deviation, since it's a square root, right? It's square root. It still retains the original measurement. So the original age was given in years. Standard deviation also will be in years. If the original unit is in centimeters, standard deviation also will be in centimeters. So it retains the original measurement, and therefore no intelligence is lost, and it makes sense also, right? That's kind of what it means in terms of standard deviation. So that's kind of what is the purpose of standard deviation and why we need to take the square root, kind of an extra shot over there. And if you want more extra shots, you can go through this link for extra reading. There, if you see, there is an example that they talk about, a pizza example. I'll just quickly read through that. What they say is, a shop delivers a pizza in 20 minutes. That's an average shop. So most of the times this shop delivers, let's take Domino's, okay? They deliver pizza in 20 minutes, okay? That's what they do. And they also say that the standard deviation is 5 minutes. So what does it mean? Most of the times it's going to be 20 minutes, And in case they are late, they are going to be late by standard deviation of 5 minutes. So they are not going to be more than 5 minutes late. So at the most, it might be 25 minutes. From 20 minutes, it might go to 25 minutes. That's what it means. So that's kind of the context you need to put instead of simply calculating the standard deviation. When someone talks about standard deviation and why it is important, that's a perspective where you put, okay, 20 minutes is the norm time. At the most, if they are late, they are not going to be more later than 5 minutes. So if you add those two numbers, 25 minutes is going to be the delivery time. And similarly over here, the age, if you see, for UK, it's roughly 80 years. We can round off, let's say we can 80 years, and the standard deviation is 14 years. So most of the men in UK live long for 80 years. And at the most, if there is any deviation, it could be plus or it could be minus, but at the most it can go within this plus or minus 14.7. So it might be either 94 years or it could be 76 years, something of that sort, the lower and upper range. So that's what it kind of means. So with that, that's a wrap up on why standard deviation, how standard deviation, and standard deviation pretty much is a square root of variance, and it retains the original unit of measurement. That's kind of the key takeaway, and we'll see you in the next episode.